Hi everybody, welcome back to this STM32F1 tutorial within the SPI communication. So far we have been transmitting data using the SPI communication, and now this is a good timing to use the SPI for receiving data from other devices. And nothing better to show this through an example, and we are going to create from scratch a library for the NRF2401, and we are going to use the SPI. This is the part 1 of this tutorial. So to have an overview about this tutorial, we are going obviously to use two NRF because it's a radio frequency communication, and this NRF will be connected to two separate STM32F1. And the first part of this tutorial, we are going to introduce the NRF24 and set up the communication between the STM32F1 and the NRF. Then we are going to understand and set up the NRF24 for radio frequency communication, and also prepare the receive mode at the NRF24. Finally, at the third part, we are going to set up the NRF24 for transmitting the data and having an example to put everything together. So this tutorial is focusing on introducing the NRF24, and also we will set up the communication with the STM32F1. So by the end of this three-step tutorial, you will be able to create a library from scratch for the NRF24, where you will have a primary transmitter and a primary receiver. So the primary transceiver will be initiated each time using this push button. So each time I will be pushing this push button, the primary receiver will receive some message and will toggle this LED here, and after that we will see in both the UART communication, where the COM3 is the receiver and COM7 is the transmitter, we will see kind of a debugging message. So let's push. So you see, when I push this one, a signal has been sent to the NRF for the receiver mode, my LED has been toggled, and I receive the message hello WeeW, and in the transmitter one I received message sent successfully. So if I push again, my LED will be switched again to off because it has been toggled, and I'm receiving the same message. Before jumping to the video, let me take the moment and thank everyone for their support. I will keep doing my best to provide this quality content. So as usual, to support the channel, you can give us a thumbs up, make a comment, or subscribe, and stay tuned. Okay, so as usual, all the code that we are going through is available on the GitHub. You can find the link in the description below. The code that we are going to use is purely C, and the program that we are going to use to load the program, to compile and load, is Kale, the version 5. So we are going to use a freeware which is HTML, which is used for interfacing UART communication between the STM32F1 and the PC. Finally, the level that you will need is a kind of a wheel level, as we are going to use GPIO, SPI and UART library. However, there is a lot of information about the NRF24 and the communication that would be used with whatever the microcontroller. So this is also an opportunity for people who are using a different microcontroller to get introduced to the NRF24. Okay, so the hardware that we are going to use within this tutorial, so we will need the STM32F1, or aka the blue pill, also the FT232, which is a device that we be using for interfacing the UART communication between PC and the STM32F1. Finally, we are going to use the NRF24. So let's go quickly through the main title of this tutorial. So first we're going to introduce the NRF24, having an idea about how it works. Also after that we are understanding the 8 pins, because there's 8 pins in the NRF small part that we are buying, and we need to understand which pin is doing what. Also, we are going to understand the PIC connection with our microcontroller and which one we are going to use. After that, we are going to the coding, and first we need to have an initialize function with the STM32F1 and the NRF. After that, we are going to read, making a function that will read the registers of the NRF24, and after reading we have to write, and finally we will create a general function that will make some comment for the NRF24. Okay, so now that we went through everything, let's have a quick introduction about the NRF24. So the NRF24 is first of all a transceiver, means it can receive and transmit. It has a lot of channels that we will see later. So it operates at 2.4 gigahertz, which is an open frequency that can be used internationally, and can send the data at 250 kilobyte, 1 megabyte, and up to 2 megabyte. And you would have 126 channels, so it goes from 2.4 gigahertz to 2.5 something gigahertz. So and this is quite really big band that you can use. But for when you use a 2 megabyte, you have to read carefully the datasheet of the NRF, as it needs some specific setting, because it can create some noise and problems. Okay, so one NRF can receive from 6 other NRF, so it has 6 parallel data type, which is really great. Also, it can operate or like a voltage support from 1.9 to 3.6 volt. However, you have to be really careful with this small part, because you may find sometimes some noise issues. So there is some special treatment that we will go through in a part 2 of this tutorial, how to have to avoid any risk of electronic pollution or parasite. So we will take a look on it. And also works with SPI communication and can work up to 16 megahertz crystal speed. Also, in a power consumption, it can go to 11 for TX mode, 11 milliampere. For receiving mode, you can go much further, and we will take a look more in the part number 2 of the tutorial. Finally, the price can be varying between $1 to $2. To be honest, the one I'm using is less than $1, and it's quite cheap, so it's quite nice to have some of them at hand. Okay, so now let's take a look on the pin layout. So there's an impressive 8 pins that we do have in the STM32, in the NRF24, and you can see here in red, you can see the numbers of the pin. So usually you can see the ground, it's within a white square, so you can locate it easily. And near the ground, on the left of the ground, on the right of the ground, actually, there's the VDD. So it's always very simple. Mark, there's the ground and VDD, or the supply power together. Besides under them, you do have the CE. The CE one is a pin specific to the NRF24, which is something that activates if you would like to be receiving on transmitting mode. We will see this more in detail when we will go in the next tutorial. After in the right of the CE and the right of the CE, you do have the CSN, which is purely a SPI chip select pin. And on bottom of this two, you have the clock and the MOSI, and which is also purely SPI. Finally, in the at the back, you do have the MISO and IRQ. IRQ pin is a really powerful and good pin, because this IRQ pin is the one that will make an interrupt to your microcontroller when it receives or sends or some special status related to the NRF. So instead of each time going to inside the NRF and looking for the data, you can just set up and get the signal that something is happening, so your microcontroller is not wasting time looking each time on the data for the NRF. Okay, so let's take a look on quickly how we are going to connect with the STM32F1. So here you do have the picture of the STM and the NRF. So CE will be connected to PA0, CSN as a clock, MOSI and MISO are connected to the SPI1 pins of the STM32F1, where IRQ will be connected to PA1, VDD to 3.3 volt and the ground to the ground. Okay, so we have been looking to and getting some idea about how the NRF. Now there is nothing better to start really coding and have fun. So here we are at our initial empty program where we are going to start making our code. So just for your information, I added the SysTick library, the GP library, SPI library, UART library too. Also there is the NRF C and H file, the library which is actually totally empty, where I just added the previous library just to use them later on. But in general, this is the empty library and we are going to set up later. Okay, so now let's go jump and start creating our NRF library. So what we are going to use, we can immediately use the same exact library we used for the SPI init, where we are going to change a little bit one parameter. So we can just copy paste this one, copy paste the SPI init that we do have. So we go to here and we copy, and instead of SPI init we can add here NRF init. Okay, so this is NRF init, and what we are going to change is a small thing. So in our SPI init we put at the minimum clock speed, which is FLK divided by 200, the F clock divided by 265, and that's what the parameter that we are going to change right now. So we can use the SPI library at the maximum speed and at the maximum speed of the NRF24. To say so, to look for it, we can go to again to the reference manual that we do have and quickly jump to SPI. This is something we have been looking for before. So if we go to the SPI and the control register 1, so let's go to control, this is I2C, sorry, not SPI, SPI register, yeah, control register 1, and the baud rate, this 3-bit, are controlling the SPI speed. So we would like to have the F clock divided by 8, which should be 9 megahertz, as our clock is 72 megahertz. So, and if we divide by 8, it's 9, so that would be fine. By 4 it becomes 18, so it's above the maximum clock that the NRF24 clock speed can handle. So we need to have 0, 1, 0, which means we need to implement here 0, 1, 0, which are on the other term a 10 hexadecimal number. Okay, so instead of having the hexadecimal 31, we will be 10, and that will be divided by 8 here. And same for SPI 1, 10, and this one will be divided by 8. So we have quite a better and faster speed to manage with our clock. And also we do have our NRF, so we just need to copy this one and put it in our clock here. Let's put this and add an extra line, should be fine. So let's go back to our code and paste it also here. So let's, after starting the NRF communication, let's put like this one, and for the SPI we are going to use the SPI 1. Let's put SPI 1, and if I save, I have to remove the void too. Okay, let's save, compile, and see. Okay, one morning, I'm quite sure that's I didn't add here an extra line. We should be now good to build our code again. Yeah, it's 0 error and 0 warning. So we do have our initializing, the first part of init library is ready now. So now that we finalized the first part of initializing the library, we can jump and try to read from the NRF24. So within this part, we are going first to optimize our SPI library to have a better dry or do not repeat yourself function when we about selecting the SPI. And also we are going to get introduced about how to communicate with the NRF and how the NRF is working. So in this part, before really jumping into really start coding and everything, there's nothing better to take a look to the reference manual or the preliminary product specification for the NRF24. So actually, this is a really great document. I really advise you guys to go through it. There is a lot of information and a lot of understanding about the NRF is working. But the main idea is there is this chapter where we do have the register map. The register map is a list of registers. All of them, most of them are 8-bit registers, and they do have an hexadecimal address going from 00 to 1D. And for each register, you do have some bits, sometimes it's a group of bits, that you will be handling and managing to control your NRF. So for example, this is the configuration register, and so you do have this power up bit. So usually, or as a reset value, it's a 0, and if you put to 1, then the NRF will wake up. This is one of the example. You can see there is a big list of registers here, where sometimes there are 4 bits that you have to change, and change the retransmitting speed. This is all that we are taking a look later on, and so you can change the register's value, so you can control the behavior of your NRF and also how the way of sending and receiving the data. Okay, that's really good. That's actually quite great. However, you would tell me, how would I read the register and how would I write in register? So first of all, let's take a look to the data control chapter with SPI operation. So you can see here that to read a register, there is a command, and this command shows like whenever you send this char, which is 000, and then at this position, the AAA, you put the register map, the register address, you will get the value. And that's the same for writing a register, but you have to put 001. We will take a look quickly on this one, and later more detailed about managing this one. Okay, so and to make a reading operation, so if you go a little bit here down and you start taking a look, so this is SPI reading operation. So as far as you do have a chip select and your signal goes low, first you will be sending the clock and your instruction. So this is actually the instruction here, and so what the master output, so you will be sending your master output. Then your NRF will not really care about what you are sending and will be sending the value of the register that you asked for within this first operation. We will take a look on the example together, but first one, you will be sending this data, and then the NRF in the next one will be sending you the register data. Okay, and be careful, you have to go back high, else the NRF will stay just sending the same data for this. Good, so now we have an idea how about the SPI operation works. We have to go back to the STM32F1 reference manual, and we take a look to the status register, because we are going to read data. We have to wait for the data to be ready, and this bit here, the bit number 0 of register still busy or not, which is here, the receiver buffer not empty. We have to wait until this bit is cleaned and become 0. Okay, so let's start, and we will go to change our SPI library and create 2 small functions that will help us to have a very dry code, or do not repeat yourself code, to be used in the NRF library. So the first one, we are going to create this one. So this is will return a char, because this is the one of reading the data. So what we will do is a char, and we will call it SPI Rx, and what we will use is here we will need unsigned short as usual, which is SPI, and also we will need a char, the value that we would like to send and to get something later. So what we are going to use here, it's a simple easy operation. We will put if SPI is equal to 1, we close the parenthesis, and what we are going to do, we are taking the same thing first as transmitting. We are taking the same thing. Let me put this one here and change this tx char to value, the value we are sending. Okay, and just before that, we have to specify the return value that we are going to add. So char rx val here, and this is the value that we are going to read, and also that will be the value that we are going to return. So return this one. Okay, perfect. I added twice. So we have been here in the first line that we have for the SPI1, we have been sending some data, but we need to read the data. To read the data, so after sending it, and we are not busy anymore, we are going to use, so instead of waiting until it is busy, we are waiting until the receive is not busy, and during that time we are going to read. So we use this one, the Rx value will be equal to the data register. So we will keep reading the data register until it's not busy. Okay, so now we finish this one, quite very simple. Then we can quickly jump on the chip select SPI. We can put char here and SPI CS, and we just need to input two things, so both unsigned short. First one is SPI, second one is also unsigned short, and we will call it low high. Okay, so we just, yeah, I forgot for the receive also we have to put the else. We have a complete example. Else it's equal to 2, and we change everything to 2 here. 2, 2, and 2. It will be exactly the same for this one. So let's put like this one. We are removing most of the data here because it's a different way of approach. And we are going to copy this one here, because this is for the SPI1, this is chip select that we are going to use here. So let's put this one and put low high. Okay, so it will take the value, else it will be the chip select that we are going to use, which is the JP4. Okay, the B12, port B12, and we put here low high. Okay, so now we set up something ready for our SPI, and we are good to jump the code for the NRF. Okay, let's final check. Yeah, so far looks good. Let's save. And yeah, another small thing, quite helpful for you guys. I just prepared the list of, so you can see if we go here, and you can see we do have not this one. If you go here, so we do have this command, and instead of just writing all this one or all this one, I already made a list, so we can just use the names, and the value is related to this register, and also the value of some of the bits here. So let me add it here. So you can see here all the NRF register that we are going to use are already copied, and also some of the change that we would like to make later we will take a look after more in detail. But you can see, for example, NRF read command, which is 1F, which means here if I go back to my here command and SPI operation, so I will put and operation with 1F. So as far as this one are fine, the other one will be 0, 0, 0. Okay, let's go here, let's save this one and prepare my my function. So it's a char because it will return some function, and we call it SPI, not SPI Rx, but we call it NRF, this one, NRF command, and it will be an RD for read. Okay, so we will add as usual unsigned short SPI, and also the char of the register that we would like to read. So register address. Okay, let's start writing the code here. So what we are going to do is to first we are going to return this chart NRF SPI, actually SPI read. Okay, and if we go here we are going to return it. Okay, let's return it so we don't forget about it. Okay, perfect. And after that what we can do, so yeah, I have to add this two wonderful small function to the header file, like this, and also like this. Yeah, so we do have our header file and function ready to be used. And if we go back here, so SPI chip select, we are going to use SPI1 and we are going to go low, and then SPI, same SPI chip select, and we are going to use 1, and we would like to go high after that as soon as we close this. And in between, first we are going to send, so SPI Rx, and we are going to send to SPI1, and the data that we are going to send will be the register address, and the function here, the NRF read, to avoid any problem for the command. Okay, so this is the first one. This is the first time when we start reading. Okay, something is getting wrong, expected, yeah, because I have to close this one. And after that, the second time when I'm going to read, I will be just putting equal and adding this one. Okay, and that's all. We finish reading our data from the NRF. So let me save this one and take it to the header file. Okay, our second function, and let's add here. So to read this one, let's make a good example. Okay, so let's here go and use a for loop. So we do have around 30 register, but we are going to read only the first 9, just to quickly and to quickly read them and not get confused. So for I equal to 0, I less than 10, and finally I plus plus, we are going to read this register. So for the SPI, we are going to use SPI1, and the register number is I. However, this is good, but we really need to debug and understand that, and that's here where the UART library comes in. So we'll put UART TX, and we will put 2. So we are going to send the data using UART data. So what's happening here? UART is not declared, probably because it's capital letter UART TX. Yeah. Okay, and let's use the UART TX to get a better picture. So what we are going to do is this one, we are sending the I to know what number of register we are tracking, and also here we can add, just to put a small distancing against the value. And finally, let's add a new line each time we read the data from the register. Okay, so let's add a new line. Okay, I think now the code is ready. Let's save and build to see if there's any issue. So probably this is a new line problem that I have to add here. Here is fine. Here is not fine. Exactly. So if I build again, one morning, probably SPI missing statement. Where is it? Ah, yeah, this is a void. We don't really need to have any input on this one, so we can change this one and put it void. Okay, it's not really a terrible problem. Let's build 3 error. Okay, what's happening here? We do have a 3 error here, so char. Oh, probably I changed the wrong one. So this one is a char, but this one is a void. Yeah, let's run. 0 error, 0 warning. So before running the code, let me show you the configuration. So you do have here, you can see there's all my microcontroller connected to the NRF. One of them is connected right now, and for actually both are connected, but they have no code inside the microcontrollers. And what we are going to do is to start reading the data from the NRF using the UART communication. Okay, let's load the code and take a look on what we are going to see. So let's read this one. Okay, so better to show you when I load the code what happened. Okay, so there's start NRF24 communication, which is the UART sent here, and then I'm receiving the list of the 10 first registers. Let's quickly analyze the first one, and then we will compare against the preliminary data sheet or the data of the registers. Okay, so the first is the 00 or 0. That's the first one that we sent. So this is register number 0, and then I just put the space here, and after that, let me try to make it bigger. No, I can't. So, and this is the value of the register, and finally the new line. So we can read only the code like this, or I'm adding both so we can see just the difference. Okay, so let's take the preliminary file and compare against the register map to see what value are we reading and if we are reading the right code or not. Okay, let's go here. So the first register 0 should be 0000100, which is a 08, a 08. Next one, we just have 2 zeros on bit 7 and 6, so it will be 3F. So 111 means 3, and this 111 is F. Perfect. The next one, register number 2, we do have only bit 1 and 0, so it will be 03. 03, perfect. And register number 3 is also a 03, 03, 04. We have here 032. Let's check 04. Exactly same. Let's go 05. 05 should be equal to 2. 05 is equal to 2. And then we go to 6. 6 should be here. So we do have 1, 1, 1, and this one we don't care. And we do have 05. Which one? This is a 06. It's a F. So we have 1, 1, 1, and then all the rest is 0. So perfect. For the status register of number 7, it's very important register. We have 111 here, 0E, perfect. 08 is a 0, 090, both of them are 0. So we do have quite a proper working reading function. So we just completed reading the data from the NRF. So the next step is to start writing and changing the registers that we have been exploring in the previous step. Before jumping to the code and start really coding and changing the register value, let's take a look again how we are going to go through writing operations. So if we go to SPI operations here, so to write an operation or to write in a register, we have to send this command plus the address. It's almost same than the reading one, but there's a small difference from the reading. So in the writing operation that we do have here, you can see exactly. So first we send the command about the address plus the address and the command. After that, the NRF will stop really sending the data, or the data sent by the NRF will not have a lot of meaning because it will be listening to the code that we are going to send. So first sending the command and the address, command for write of course, and then it will be start listening and updating the address as we are going to write in it. Okay, so the next thing is to check a little bit about the strategy about how we are going to update. So what we are going to do is, for example, this is like the address here is simple, but on one of the strategy, let's take which example, this one. This is the setup, the retransmission setup register. Okay, so this register is used to say how much time the NRF should be waiting before retransmitting if the transmit has failed. So here there is 4 bit at the end of the register that we would need to change. Imagine we set up at the first place that the retransmit time is 0010 and we would like to change it to 001. So what we would like to do first is to set everything to 0 and then set to the desired register. And to set up everything to 0, then to put, we are going to apply a mask. And that's how we are going to do for changing the value. Then there is another important thing. So before writing into register, we need to read the whole value of the register, because this register already have a certain value in the other part of the bits, and we don't want to mess with this value. So first we download all the register, we apply a mask on this value, and then we update with the desired value. We can after that, only after that, we write the value into the system or the NRF24. Okay, based on this logic, let's start writing our function. So also for this function, normally we can put it as a void, but I'm putting it as a char which will return 1 or 0, and this is just to have a kind of idea if the change has happened or not. So we put char NRF command and write. So as usual, we will use the unsigned short. Okay, the SPI, and after that char for a register address, and then we will have a new value, so char the new value that we would like to apply. Finally, the mask related with the new value, so char, and we call it mask. So I know it can be a little bit complicated or overwhelming. Feel free to send me your question in the description area. I'll be happy in the comment area. I'll be happy to reply. So to go with that, so we need some local variable, so reg value, and this is the address that we are going to download to get this new value for the value of the register. New register value is the new value that we are going to create based on the new value we are applying for the register. And finally, the command value that we are going to use and to send our code. So command is equal, so NRF write, which is the command for writing the into the register for the NRF. So it will be NRF write, okay, and it will be parallel with the register address. Okay, after that we are going to read the register value, so we are immediately going to use this function directly here and paste. So instead of putting the I, we are putting the register address, so we can get directly the register value. After that, the new register value will be equal to, so the register value, reg value, where is it? This one, so let's put it between brackets first, and the mask that we are going to use, and this is parallel to the new value. That's how we are going to create the new value for the register. So we finish this one, we copy almost the same code here that we do have, exactly. So first we are going to put the command here that will say that we are going to write in a certain register. If something is getting wrong here, yeah, an extra, this one. And after that we are not going to read because we don't need to read, and we are going to send the new register value that we would like to have. Okay, so now we already finished and we wrote all the code that we need to have. However, as I said, I would like to return and see if it's true or false. So what we can do, we are going to read again the register value here and going to compare it. So if my register value reg value is equal to the new register value, then I can return 1, else I'll be returning 0. Okay, so we can have kind of a binary function that will give us yes or no, so just to use sometimes for quick confirmation. Okay, good. So we have our function ready, and let's add it to the header file. So we go to the bottom and the function. So now nothing better to go through a small example and change a certain register. So let's take a look, and there's a quite very simple register to change. So we can change the config register and move from this one. So we are from the primary receive, which is now we are a primary transmitter, and we are going to become a primary receiver. We will take a look actually more in detail about this register in the next video. Okay, so that's the part that the register we would like to change. So if I go here and take a look to my register, so you can see right now it is 08, and if we change it, so if I go to this one, so 08, because only this one is set to 1, so if I set this one to 1, it should become 09. So let's go here and let's give the function that we have been using. Let's make it bigger first. So SPI, we are going to use SPI1 for the register address. That's the NRF config register that we are going to change. Now let's add this one just in case. And the new value, so already have the one, so this one is a prime. We would like to put it as a primary receiver, and this is the new value, and the mask is a primary receiver mask. So let's save. You should not have any error, but still, okay, they say there is a parameter missing here. Okay, let's check. NRF type 4 command write. Probably this one looks fine so far. Okay, yeah, I should not add the char. Okay, so if I save, let's go here, and so you can see now the register address 0 have the 08 value. So if I save and build, then run, it becomes 09. So you can see how easy you can change the register. And if you would like to change it again, so if I remove this one and try to read data from my register, if I go like this, so it stays 09. It's saved in the memory of the NRF. So what I have to do again, if I would like to change it back, I have to write the value. So instead of primary Rx, it becomes a primary TX. By the way, again, all this data is in here. So you can see here that we have the primary Rx and the TX and the mask. So if I save, run, build, and update, it becomes 08 again. So with this operation, we are able to read and write in the registers of the NRF. We completed the write function, which was quite a tough one, but I think now we are clear about most of the code. So we can jump now on the NRF command, which is a really simple one, but we are going to use for the purpose to use a pure command for the NRF. Okay, so we are at the last step, so the NRF command, and let me explain to you why I would like to create this special function. So the NRF command is exactly same as the write function, the read function. Let me go SPI operation. So, but in the read operation, we have to use the read register command. So what we are going to do is to use this one using the read function, but without having the read register. So this is more function to use to input some data to flash DX or RX, and also reuse something. So this is the other command that sometimes we will need to use without having this read register coming up. Okay, so what we are going to do, so this is a quite really simple one, extremely simple one. So this step, so what we put here, and instead of NRF command read, we are going read command, and the only difference, we are going to remove this register here. We are not needing this one anymore. Even the parentheses, we can remove them. And for the register address, we will change it. We will call NRF command. It's more talking here, or let's call it command here. That will make more sense to change it like that, the command. And here we have also to change the command also for this one. Okay, then that's all. This is the function that we are going to use in the next parts of the tutorial, but we just need it right now. It also returns sometimes a certain variable that we will see too. I think that's all for this tutorial. We have been seeing so far the read function, so we could initialize our NRF. We could also read some register, change also the other registers. Finally, we have a command, a general command function that we will use later.